Hello everyone, we're finishing up the second video on part 2. We did completely randomized designs last time, so let's go right away to randomized block designs. So, what do you do if you can't have so much replication? That was what made a completely randomized design so effective, but sometimes you simply don't have that many subjects. Let's take a hypothetical small experiment. It's in the TigerStats package, so again, to get a close look, run the data and the view commands. The basic idea is that you have 16 subjects who have agreed to be part of an experiment to compare two weightlifting programs, Program A and Program B. Let's go ahead and take a look at this data frame. We find it in the source files, and looking at it we see that we have the name of each subject as the first column. We've also recorded the sex of each subject. There's 8 females and 8 males, and we've recorded whether or not the subject is a varsity athlete. 8 of them are athletes and 8 of them are not. Now, you could try a complete randomization for your group of subjects, so you might decide to randomize them into 2 groups of size 8 each, and the first group would be given Program A to work with for some period of time, and the second group would be given Program B to work with for some period of time. And then at the end of that time period, you might do something like measure the increase in strength for each person and compare the average increase in strength for the 2 groups. So of course that could be done with the randomexp command. And let's go ahead and give it a try. We'll do it without a seed, so that every time that we run the command, we'll get a different randomization. And our question is going to be, does it look like the groups are always looking similar? Is complete randomization reliable at making the groups look similar? So we copy, we head to our studio, we paste into the console, and we give it a try. So this time we appear to have done pretty well. If you look at the 8 persons assigned to Program A, 4 of them were female and 4 of them were male. And furthermore, 4 of them were athletes and 4 of them were not. It looks like we got things just right with regard to sex and athletic status. The 2 groups look similar, at least with respect to these 2 variables that we happen to measure on every subject. That's pretty good news. Let's give it another try. Use the up arrow key to get the command again, run it again, and let's see how things come out. This time, not quite so good. We have 5 females and 3 males assigned to Program A, so that means there'll be a similar slight lopsidedness for Program B, only 3 females and 5 males. We've also got some lopsidedness in athletic status. Looks like there's 3 athletes in Program A and 5 non-athletes in Program A. That's still not too bad. Let's give it another try. Up arrow key, we have the same command. Run again, we'll get a different assignment. This one looks okay as well. Looks to me like we've got 4 females and 4 males in Program A, and we have only a slight imbalance in athletic status, 3 athletes and 5 non-athletes. Let's give it another try. And this time, it looks like we were mostly okay with respect to sex, 5 females and 3 males, but it's not looking too good with respect to athletic status. Program A has only 2 athletes and 6 non-athletes in it. And then Program B is similarly lopsided with respect to athletic status. If you go ahead and keep trying this yourself several times, and you'll find eventually there are occasions when the 2 groups can be quite different, either with respect to sex or athletic status or both. So the groups don't always look similar when you use complete randomization on a small number of subjects. So what do we do to get around this problem? There is a partial solution available, and it's called blocking. The first step is to create blocks of subjects that are very similar. This is where you use your judgment. So you happen to have measured the sex and athletic status of every individual, so you could form blocks that are very similar with respect to these two variables. You could make a block consisting of the 4 females who are athletes. There's another 4 females who are not athletes, and you could make them the second block. Now, of the 8 males, there were 4 who were athletes. You could make them the third block. And then the remaining 4 males, who happen not to be athletes, you could make them the fourth block. Within every block, people are similar, at least with respect to sex and athletic status. Then you leave your judgment and you let chance take over. That's step 2. Within each block, you randomly assign subjects to the 2 groups. So take that first block, the 4 females who are athletes. 2 of them will be picked at random to go to group A, and the other 2 will go to group B. And you'll do the very same thing with each of the other 3 blocks. So for the second block, 2 will go at random to group A, and the other 2 will go to group B. For the third block, 2 of those guys will go at random to group A, and the other 2 will go to group B. And then in the final block, 2 of those guys will go at random to group A, and the other 2 will go to group B. That's a blocked randomized design applied to these subjects. The way you can do it with code is again with the randomexp function. You apply it to your data frame of subjects just as before. You specify that you want 2 treatment groups just as before, and you specify their sizes. And remember, the sizes need to add up to the number of subjects available. There's a groups argument just like before, where you give the name for each of the treatment groups. But there's a new argument, and it's called block. And what you do is make a list of all of the variables with respect to which you plan to block. You plan to block with respect to sex and athlete, and so you put those 2 into a little list and feed that to the argument block. The great thing about this is that at least the variables sex and athlete have no chance to be confounding factors, because the 2 treatment groups will look exactly the same with respect to sex and to athlete. Now, if you were doing this for real, in an actual experiment, you would set a seed first using some familiar unit number. I chose to use the birthday of my middle daughter, so that everybody knows exactly how you got your assignment done. But we're going to go ahead and run the code without setting the seed and run it several times just to confirm for ourselves that the groups look similar with respect to sex and athletic status, even though they're different with respect to the actual individuals that go in them. So we'll copy, we'll head to RStudio, go down to the console, paste in, run, and notice we have 4 females and 4 males in each group. We have 4 athletes and 4 non-athletes in each group. We even have a complete matchup. There's 2 female non-athletes in each group, 2 male non-athletes in each group, 2 female athletes in each group, and 2 male athletes in each group. Let's use the up arrow key to get the command again, run it again. We get a different assignment of people to groups, but we get the same with respect to sex and athletic status. In each group, there'll be 2 female non-athletes and 2 male non-athletes, 2 female athletes and 2 male athletes. Here's a real-life example of blocking. It comes in the data frame Saltmarsh available in the TigerStats package. You can view help to see where the data came from. When you look at the data frame, you see that it has 24 rows, 10 of them are displayed here, and there are 3 columns for 3 variables. Each row corresponds to a little plot of land at an agricultural research station. And the first column gives the amount of salt that was artificially put into the plot. There were 6 possible levels of salinization: 10 parts per million, 15 parts per million, 20 parts per million, 25 parts per million, 30 parts per million, and 35 parts per million. Those were the 6 possible values of salinization. Now, the second variable, biomass, gives a measure, and I'm afraid I could not find out the units, but a measure of the total biomass present in the plot after the period of study had ended. We have a third variable called block, and it has 4 possible values: field 1, field 2, field 3, and field 4. So what was going on with this data set? Well, the research question that people had in mind was this: does the level of salt in soil affect how much plant life grows there? At this agricultural research station where the experiment was conducted, there were 4 fields available for use. Now, these fields were different with respect to where they were located, with respect to the angle they had towards the sun at that time of year. The wind conditions were different. Probably the soil was a little bit different, and so on. So the fields differed in lots of ways that could have an effect on how much plant life could grow in the field. So it would be natural to treat each field as a block. Each field, each block, was divided into 6 equal plots. And then, within each field, those 6 plots were randomly assigned to the 6 levels of salt. So this is kind of interesting. 6 times 4 is 24. So they're going to end up being 24 plots, and that's why there were 24 rows in the data frame. Each plot was a subject in the experiment. The subjects in this experiment were actually created during the randomized block process. Just by looking at the data frame, you can tell that blocking really was done. Looking at the relationship between the variable salt and block to see how things turned out, you can run the xtabs function, and you'll find, sure enough, that for every possible value of salinization, each field was represented once. Or another way of looking at it, in field 1, each of the 6 plots was given one of the possible salinization levels. Here's a quick look at the results from a descriptive point of view if you're interested. Since both variables, salinity and biomass, are numerical, you can make a scatter plot to check on the relationship. It seems that when salinity was low, say 10 or 15 parts per million, then biomass tended to be somewhat high. But when salinity got to be 20 parts per million or more, the biomass was lower. Randomized block designs were the second type of experimental design that we've looked at. There's a third type that really contains 2 subtypes. So we're looking now at matched pairs and repeated measures designs. Matched pairs aren't really anything new. They're just an extreme form of blocking in which each block contains exactly 2 subjects. So you can use one when you plan to have 2 treatment groups. For each of these pairs, you randomly assign one member to group A and the other to group B. Usually what you're interested in is the difference between the values in the response variable for the members of each pair. The idea, when you use your judgment to choose these pairs, is that the pairs should consist of subjects that are as alike as possible amongst all the subjects. A classic matched pairs example has to do with this research question. Say you're a shoe manufacturer and you're looking at two types of shoe sole, A or B, and wondering which one of them wears out more quickly. And say you have 20 people who agree to participate in an experiment. There are 20 people, and 20 people would presumably have 40 feet. The subjects in this experiment won't be people. They'll actually be the 40 feet. But those 40 feet naturally come in 20 pairs, and members of each pair are very similar because the pairs of feet will be feet that go with each person. So, the way you randomize after you've blocked is that for each person, you pick one of the feet at random to wear sole A, and the other foot will wear sole B. The reason this is such a great design is that the members of each pair are very similar in the kinds of wear that they're going to put on shoes. If a person is active, both of those feet will be subjected to a lot of that activity. If a person is sedentary, both of those feet will be pretty sedentary. So when you look at the difference in the wear in the soles on each foot, if you find big differences on average, you can probably ascribe that to the type of sole and not to differences in activity levels of people. Now, repeated measures design is similar to a matched pairs design in the sense that there'll be pairs of measurements and we'll be interested in a difference. However, in a repeated measures design, each subject is actually measured twice under different conditions. We'll be interested in the effect of those conditions on the measurements. And again, we'll be interested in the difference between the measurements. Let's look at an example of a repeated measures design that's present in the TigerStats package. It's the data frame labels. After you run data and view, you can see labels in the source files pane. Let's take a look at it. It's a data frame with 30 rows and 3 columns. Now each row is a person, a subject in an experiment, and the columns are variables that were measured on the person. Let's talk about the background for this experiment. It was done at Georgetown College by a couple of students in Math 111 some years ago. The students were interested in the following research question. Does the type of label that appears on a product affect people's perception of the quality of that product? Or are people's ratings for the quality of a product entirely based on the inherent quality of the product itself? So the students got 30 of their friends to agree to be part of the study. Each friend was taken one at a time into a room and sat down at a table where there were 2 jars of peanut butter. One jar had the usual Jif label on it, and the other jar had the Great Value label on it. Now, Jif is a famous brand name for which there's a lot of advertising, and it is a somewhat expensive peanut butter. Great Value is the Walmart brand, and it's generally known to be cheaper. Now, each student was asked to participate in a taste test, to taste a little mouthful from each of the jars in turn, and to give the mouthful a rating on a scale of 1 to 10, where 1 is lousy and 10 is I absolutely loved it. So the rating the student gave to the jar labeled Jif was called Jif rating, and the rating the student gave to the Great Value peanut butter jar was called Great Value rating. Now, what the students in the study did not know was that actually both jars contained exactly the same peanut butter. It was the Great Value peanut butter. So, if your perception of the quality of a product is unaffected by the label that you see on the jar, then it seems you ought to give the same rating both times, since you're tasting the same peanut butter both times. Now, I have to back up and qualify that a little bit. It could be that your perception of the taste of peanut butter changes on the second mouthful from the first mouthful. So what the students were careful to do is to randomly have half of the students taste from the Jif jar first and the Great Value jar second, and the other half tasted from the Great Value jar first and the Jif jar second, and that was an attempt to wipe away any possible order bias. When you do that kind of order variation, it's a good idea to record for each subject which order they took the peanut butter in. Unfortunately, the students did not do this. There's no variable that you see here that records the order. So you might be interested in seeing the results of the experiment, at least descriptively. This is repeated measures. Each student was given 2 ratings. So you're interested in the difference. How do you compute the difference? You want the difference between the Jif rating variable and the Great Value rating variable. So the way you make R do this is first tell it how to find the Jif rating. Since it's inside the labels data frame, you can say labels and then $, and then the name of the variable you're interested in. That tells R to look for GIF rating inside of labels. Now we have a minus sign, and then we have labels $ great value rating. And so R will locate each of those two variables inside the labels data frame, and it'll subtract the great value rating from the GIF rating for each subject, and it'll produce a new variable that has 30 numbers in it, 30 differences, and we decided to call them diff. Now you can study diff. For example, you could take fave stats on it. You still use a formula, twiddles diff, but you don't have to give a data argument, because when you made diff, you actually put it inside your global environment, and R knows to look there for a variable. So once we do fave stats on diff, we see, on average, the students rated the GIF labeled jar 2.37 points higher than they rated the great value labeled jar. Whether that difference is so big that it can't be just explained away as chance variation in which jar they chased first or something like that is not clear at the moment, but at least descriptively, it looks like students were giving a higher rating to the jar that's known to be more expensive. So it seems their perception of quality might very well be affected by the labels that they noticed. We'd like to take a look at some further terminology and ideas that are associated with experiments because you're going to come across them later in life. If one group in an experiment is not treated in any special way or is present just for comparative purposes, then this group is often called the control group. So in that aspirin and heart disease experiment we were talking about earlier, the control group was the group that took the fake pill. They had nothing particular done to them. So what's happening here is a comparison between people who get nothing and people who get aspirin. So the experiment really is to see if aspirin works better than taking nothing at all. Now, if the subjects in an experiment do not know which treatment group they are in, then the experiment is said to be single-blinded. Also, if the people who measure the response variable on those subjects do not know which groups the subjects are in, then the experiment is also said to be single-blinded. So there's two ways for an experiment to be single-blinded. It could be single-blinded from the subject side or from the researcher side. What are the purposes for blinding an experiment in these ways? Well, on the subject side, single blinding helps reduce bias due to subjects perhaps behaving differently depending on the group that they are in. For example, in an experiment to see whether a certain vaccine reduces the likelihood of one contracting a certain serious disease, if you happen to know that you're in the vaccine group, that you're actually getting the vaccine, then you may feel safer and more confident, and you may be willing to expose yourself to the disease in certain ways that folks who know that they are in the control group would not. Now, if the folks in the treatment group, the ones who get the vaccine, go out and engage in riskier behaviors because they know they're in the treatment group and feel safer, then they could be biasing the experiment against the vaccine. We don't want that. And so, if we can keep the subjects from knowing which group they're in, then as groups, they're probably going to behave about the same, and we'll get rid of that source of bias. Now, on the researcher side, why do we want to blind people who measure the response variable? Well, quite often the people who measure the response variable are people who have some vested interest in how the experiment is going to come out. Maybe they really, really want the new treatment to succeed. Now, when you measure the response variable, sometimes there's a lot of judgment that goes into making the measurement. If the judgment is complex enough, and you have a vested interest in how the experiment is going to come out, then your measurements could be subconsciously affected by your vested interest, and thus skew the results of the experiment towards the treatment. So to keep that kind of bias from getting into the situation, we'd like to keep the researchers, or at least the people who measure the response variable, in the dark as to which treatment group the subject is in. The way that you single-blind an experiment is to use a placebo on the subjects who are in the placebo group. A placebo is an inert substance given to subjects in the control group. It might resemble the substances given to subjects in the other treatment groups, but it doesn't really do anything to you. So the purpose of a placebo is to make the experiment single-blinded. In the case of the vaccine study, one group might get the real vaccine in a needle, but the placebo group will also get something in a needle of the same size that feels the same and so on, and the substance that they get will be a liquid that looks like the vaccine, but is really inert and doesn't do anything to them. If neither the subjects nor the people responsible for measuring the response variable know the group assignments of the subjects, then the experiment is said to be double-blinded, and that's sort of an ideal we'd like to obtain. Now, a double dummy design is a procedure to blind an experiment even when the treatments don't resemble each other at all. For example, suppose that you have this research question. Which type of smoking cessation treatment, nicotine gum or nicotine patch, is more effective in helping people quit smoking? And let's say that you have 50 smokers who agree to participate. The problem you've got is that a subject is going to know whether he or she is getting gum or a patch. Gum and patch are just too different from each other. You can't make one of them look like the other. So how are you going to get around this? The solution is really quite clever. The members of the patch group are going to wear a real nicotine patch, one that actually delivers nicotine. But they will also be told to chew a nicotine-flavored gum. It's only they don't know it's a fake gum, and so they don't know whether they're wearing the real patch and chewing fake gum or wearing a fake patch and chewing real gum. The fake nicotine-flavored gum is called a dummy for the members of the patch group. Now, turning to the members of the gum group, they're going to chew real nicotine gum, but they're also going to wear a fake patch that doesn't deliver any nicotine at all. And for that group, the fake patch is the dummy. And so we've got a double dummy design. If you set it up this way, then in neither group are subjects going to be able to tell which group they're in. So that's a double dummy design. In our last section, I'd like to stress the role of chance that's always at play in experiments as well as in observational studies. The attitudes data frame was really kind of interesting because the research questions that are generated from it are some of them studied through observational studies and some of them studied by experiment. So, for example, the research question is length of sentence related to choice of major. Remember when we looked at that research question and looked at it descriptively, we found there did appear to be a pattern in the data. Apparently, when you looked at means, the math and science majors tended to sentence the defendant to about 5 years longer than the other groups of majors did. And in this observational study, remember it was an observational study because the explanatory variable major was something that the subjects chose for themselves and it wasn't assigned by researchers. In this observational study, there was a pattern in the data. But of course, that raises the question of statistical significance. Does the pattern we see in the data provide strong evidence that in the Georgetown College population, math and science majors are harder on crime? Or could the pattern we saw in the data just be ascribed solely to chance variation in the random sampling from the population? Notice here that the question is about chance in the gathering of the subjects from the larger population. But let's turn now to a research question from the attitudes data that was actually studied by means of an experiment. Remember, the research question is length of sentence affected by suggested race of the defendant. That was an experiment because the values of the explanatory variable def race were assigned to the subjects by assigning forms to the subjects where the hypothetical defendant had different names. If you look in the data, you actually will see a bit of a pattern. If you do favstats on defendants broken down on sentence broken down by defendant race, then you see that when the defendant had a name that suggested he was black, on average he got 27.77 year sentence. But when the defendant had the name that suggested he was white, on average he got sentenced to about 2 years less. Again, the question of statistical significance raises itself. Does the pattern we see in the data provide strong evidence that the suggested race of the defendant makes a difference in the length of sentence recommended, or could the pattern reasonably be ascribed just to chance variation in the random assignment of forms to the subjects? Note that this time the question is about chance in the assignment of subjects to treatment groups. The reason we couch the question this way when we're thinking about experiments is that sometimes we have difficulty in getting subjects to agree to be part of an experiment. We can't just walk up to anyone and say, "You, be part of my experiment." So we can't always randomly sample people from a population to be part of an experiment. In those cases, the subjects who agree to be part of the experiment might not be representative of any larger population at all. And so the statistical significance question can't really turn on the random sampling of these people from some larger group. But chance is still at play for the subjects in an experiment because they were randomly assigned to different groups. And so we can still ask if the differences that we see between the groups is due to some real causation, or if it's due just to chance variation in which subjects got into which groups. So for example, in this case, is the difference that we see between the average sentences due to the fact that Georgetown College students in the study were inclined to give a little bit longer sentences to a black defendant? Or could it just be that by chance, people who were harder on crime in general just happened to be given forms where there was a black defendant named in the form? Either way, patterns in the data depend at least in part on chance. So it's really high time that we step back and learn more about how chance processes work. This is the subject of probability, and it's going to take up the next chapter of the course. Thank you for listening.